Moving into section 4.2 on logarithms is our main focus for this section. We're going to get what is the definition of a logarithm and kind of also looking at graphing these logarithm functions as well. And so I know this is going to be kind of strange sometimes at first with logarithms, but you have to remember that a logarithm function is just the inverse of an exponential function. So we're actually kind of seeking out a power when we're asking for what the answer to a logarithm is. So in the last section we worked with exponential functions, and since it is a function that is one-to-one, it would pass the horizontal line test. It will have an inverse, which is a way to undo the exponential, just like if we were square rooting or dividing when we're multiplying. All of those are inverses. So let's look at the definition of a logarithm. So for any x value greater than 0, so for any x greater than 0 and a b value greater than 0, and where b is not equal to 1, then the definition of a logarithm is that y is equal to log base b of x. This is equivalent to b to the y equaling x. Now I know that looks kind of strange, but it's basically if I have this exponential function where I have some base to a power is equal to some value x, I can undo this by doing the log of that base of the value, so this is of my answer, is equal to the power. Okay, now I like to do it this way. A lot of times I'll say, if I reverse that and say log base b of x equals y, in order to change from this into exponential form, which we will practice that, we end up doing a circle. Okay, so if I have b to the y equals x, then I get this definition. And what happens is that we're so much more comfortable doing these exponential equations than we are with our logarithm. But I want to impose upon you that it is pretty simple as long as you remember this is the power that we are seeking to take this base to whatever power to get this answer. Okay, and we'll see some examples of those and be able to change from one expression to the next in different forms. So we could also kind of do a circle in this sense with an exponential form where I do log base b of x equals y. I could get this back, okay? So interchanging between those, I want you to encourage you to kind of use that circle idea because I think that's a lot easier. Now, the function f of x equaling log base b of x is read log base b of x. Okay, so now basically the answer to a logarithmic problem is the power you take the base to in order to get the number at the end. Okay, so again, the answer to a logarithmic problem is a power. Let's first practice by taking the logarithmic function into an exponential form, okay? So this is the log form, and we're going to convert this into this exponential form, and we're going to kind of use that idea of a circle, okay? So log base b of x equals y, so we take b to the y equals x. Now, if you like to have it going in that forward sense, maybe we set this equal to 3. I move it to the other side. So if I want to take my base, 7 to what power, in this case is 3, is equal to x. So 7 to the third power equals x. And that is the exponential function that is equivalent to what we have there for the log. Now, can we go forward and do 7 to the third power? Most definitely. But that is the exponential form. Here again, if you like to have that, I like to have the equals on the other side. So move that over if you have to. And we're going to do base b to the second power equals 25. So b to the second power equals 25. Now I have an equation that if I ask you to solve for b, you would be able to tell me that that b actually is equal to 5 only. I know there's a plus or minus 5, but up here in our definition, our bases are going to be positive and our x's are going to be positive. So this number has to be positive and that number has to be positive always for logarithms. All right, let's do this last one. Exponential form is going to be base 4 to the y power equals 26. 4 to the y power equals 26. Now, again, if I were to give you this idea to be able to solve that, it's going to be really, really hard to do because I can't ever put 26 into a base of 4. So we're going to see how that we solve that. That's going to come later on. All right. Let's go backwards. What if I give you an equation and we want to write the exponential form into logarithmic form? Again, it is going to be a circle since if we go back up here, we want log base b of x equals y. So what does that look like for this one here? 2 to the 5th equals x. Log base 2, this big number is our base, 2 of x equals the power. Equals 5. So this is the logarithmic form for that exponential equation. Let's try another one. We want to do log base b of 27 equals 3. Log base b of 27 equals 3. Remember, this is always the power. The base that we have the exponent to is the little number that we have as a subscript. Okay, now if we end up looking at this guy, here comes in that natural exponential that we had in our first section in chapter 4. We're going to go log base e of 33 equals y. Log base e of 33 equals y. And that would be our final exponential form. Okay? All right, so that is what is nice to have because in order to kind of start working with these inverses and kind of getting into a form that you might like to see. And we're going to end up extending this idea to now actually evaluate and find out what is the log of these certain bases to get the value that I have at the end. Okay, so now let's use this idea to actually find some logarithmic answers to problems. I suggest writing it in exponential form. So what you have to do is kind of maybe set that equal to some letter. Call it X, call it Y, call it W, whatever the case may be. And what we're looking at here is can we figure out what power that I have to take 10 to get 100? That's the question you can have. Or writing in an exponential form, doing the circle, I have 10 to what power is equal to 100. Now, this one's really basic and getting you started here, and we're trying to figure out what power is that. Well, I can take that 100 and write that as 10 squared, and once I have this, now 10 to what power equals 10 squared? Well, then these exponents have to be the same. Therefore, this logarithm equals 2. That's the answer, okay? The answer is a power that makes that base go to what power to get this number here, okay? So again, let's try this one. I want 5 to what power has to equal 1 over 125. Now this one's a little bit trickier, okay? What power of 5 do I have for 125 would be my question that I would ask. And you might be able just to kind of finagle it a little bit. 5 to the third power gives me 125. But the problem is I have 1 over that. So we have to remind ourselves if I have 1 over this, I can bring this up and make that power negative. So I could write that as 5 to the negative 3 power. That would be equal to that 5 to some power. So the question is now that x would have to be a negative 3. If I put 5 to the negative 3, I flip it and make it positive, which in turn gives me 1 over 25. 1 over 125, excuse me. So the answer to this problem is negative 3. The answer is the power. Okay, let's try this one. 36 to what power x is equal to 6? Well, what do I have to do to get a smaller number this time, in a sense, sort of, kind of. And so, again, we're working with bases. Over here, I'm trying to get the same base here. 6 is the smaller here. So the question would be, can I end up taking this number into a base of 6? Well, just so happens that I can, because that is 6 squared. Now, taking that to the x power is going to help me, okay? Because what I have here is I can multiply by the law of exponents, these, when I have a base to 2 powers. This could be 6 to the 2x is equal to 6 to the first. So now I've got the bases that are the same, and then we can set these equal to each other. So we're going to formally do that in another section, but here we can also kind of practice that, because sometimes they're not as obvious like what we have over here with our 10 squared. So here, when I divide by 2, x is equal to 1/2. So the power that I'm looking for is 1/2. Now, does that make sense? We have to remind ourselves that a 1/2 power, 36 to that fraction 1/2 power, this was my power over my root. So that was the same as the square root of 36 to the first, which is equal to the 6 that I have, okay? So be careful, because they may not be as obvious with some of those. All right, let's try the last one. Let's set that equal to x into our exponential form. 3 to what power has to equal the 7th root of 3. Now, this is going to come back to this idea that I just alluded to with these fractional exponents. Here I have a 7th root of 3, but I want to write this as a power. So since we're coming into fractional exponents, helps us out a little bit. I'm going to rewrite this piece, but I can go backwards now and say, okay, I want to rewrite this as the power over the root as 3 to the 1/7. And when I do that, these are equivalent. These bases are equivalent. Therefore, my x has to equal that 1/7. This whole problem is equal to 1/7. The power that makes that true is 1/7. Okay? All right. So that's going from basic logs down into exponentials to find out what power makes that true. Now, there are some properties for logarithms that will help us if we recognize them, but we can always go back to this exponential form and figure it out as well. First one being, if I have log base b of b, log base b of b, b to what power is equal to b? Well, b to what power equals b is what I just said. Well, what's the invisible power here? It is 1. Therefore, if I have a base and an expression here that are exactly the same, this whole value is 1, because 1 is the exponent to which b must be raised to obtain b back. Okay, I'm going to erase this part here. Second property, if I have log base b of 1, what is it equal to? Well, I can ask myself, b to what power equals 1? b to what power equals 1? This goes back to a law of exponent rule that we have to make sure that anytime I have b, a base, number, variable, whatever the case may be, to what power equals 1, I'm hoping you're screaming at me 0, because that is correct. Because 0 is the exponent to which b must be raised to obtain 1. Okay? All right. Now, again, you can get this to come out and work them through, but if you know these properties, they go pretty quickly. Now, what if I have log base b of b to the x? So our bases are the same, except for now we have a power here instead. Well, this is actually going to, in a sense, kind of cancel itself out, because b to what power is b to the x? B to what power x is b to the x? It has to be that power. And so those two things are equal to x. And if I have a base that has log base b of x in the exponent, this is also a property that is equal to x. Now, this is going to be helpful when we solve our exponential equations to know that I can get x out of it by raising a log to the same base power, or by taking the log of this base to a power to get rid of that. So we have this for b greater than 0, and where b is not equal to 1, which are the same conditions that we had in our definition for that. Okay? All right, so let's try these 4 logs and see if we can do them with some very little work using these properties. Okay, where I have log base 9 of 9, that's where I have these to be the same. 9 to what power equals 9? That is simply equal to 1. Okay, so if you wanted to set that equal to x, 9 to what power equals 9 is the exponential equation that you could write out and solve. Notice here I have log of base 8 of 1. What is that? 8 to what power equals 1? Anytime I have a 1 here on the expression, we're going to take that base to the 0 power. So 8 to what power equals 1? That is always going to be the 0 power. Log base 7 of 7 to the 8. So we're kind of working in this property that we have right here. 7 to what power is 7 to the 8th? 7 to what power is 7 to the 8th? Well, these are going to be the exact same. So therefore, this is equal to 8. And in a sense, these things cancel themselves out, leaving me with just that power. Okay. Likewise, this property illustrates this one. Or this problem illustrates this property. And so 3 to what power, or what is this equivalent to? This base with that log, in a sense, cancel themselves out because they are inverses. This, by our property, would equal 17. So please make sure that you kind of understand that with those, because sometimes they can go really quickly, but other times it can be really, really confusing as well. So make sure you kind of have that grasp, but you can always, always, always write in an exponential form if you need to. Okay, now we're going to evolve into looking at graphs of our logarithm functions. Now, I'm going to be looking at a graph of a log. So if I look at f of x equaling log base b of x, remember that is going to be the inverse. They are opposites of each other of the exponential b to the x, okay? So we're going to kind of actually let b equal 2 here and look at the 2 to the x function and log base 2 of x, okay? And we're going to kind of figure out what that is. Now, when we talked about inverses on functions, remember on your graph, the inverse functions are going to be reflective over the line y equals x. So we had drawn some functions that are very similar, and they can be reflected over this y equaling x, showing that it is an inverse. So let's see if we can get that on our graph here, if we can get a reflective look over that. So I'm going to start by looking at f of x equals 2 to the x. So we're just going to start with the exponential kind of going forward and then look at the inverse of that. So this you practiced out of section 4.1. I'm going to look at these points and plotting them in my exponential here. 2 to the negative 1 gives me a 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 squared is 4. So these are the points that I'm going to graph. Negative 1, 1/2. 0, 1. Remember that was the key point out of section 4.1 that we wanted. And 1, 2. So over 1 and up the base amount, which in this case is 2. And I can go over 1 more. 2, 4 gives me that. So if I wanted to graph the exponential, and I'm just going to dash it for you, this is my f of x function. Okay? Now, if I want a mirror image, what's going to happen is I'm going to have a mirror image that kind of looks like this. And this is going to be the graph of my logarithm. So let's see if we can put some numbers on our log function. Now, another which the corresponding log function to 2 to the x is going to be log base 2 of x. Now, if you recall, they are inverses, have reversed points. And what do I mean by that? Remember when we talked inverse functions that the domain of f is the range of the inverse and that the range of f is the domain of the inverse. So when I have points, it's very nice that I can reverse those points to get the points on my logarithm function, okay? So again, logs aren't as familiar with you as exponents are. You've worked with those probably quite often. Logs are just a little bit of a different beast. So when I put 4 in here, we're asking 2 to what power is 4? Well, 2 squared is 4. If I put 2 in here, 2 to what power is 2? Well, that power is 1. So all of these work in our log function. These are the powers that we raise 2 to get this. So when I graph those points, I'm going to go over 1/2 and down to -1. I have the point 1, 0. I have the point 2, 1. And I have the point 4, 2. And so when I graph that function, we get something that looks like that. And this right here is your standard log function for that. Key points to remember, I'm going to kind of highlight 3 of them. Key points to remember on our exponential, we always have that 0, 1. For my log, flip that. You now have the point 1, 0 as the common point, and the base up 1. So this would be my base. This 2 matches this base that's down here, okay? So make sure that you remember that. When in doubt, you can always plot points, okay? But this is the graph that we're going to now shift around with our logs. Okay, so the domain of a logarithmic function. Notice here, we had a horizontal asymptote for our exponential. What we will have now with a logarithmic function is a vertical asymptote. Maybe I'll highlight it with in blue so we know that that's our log function, okay? Now, the domain of that log function are x's. There's nothing to the left of x equaling 0. I'm not including 0. I'm just approaching it. So anything from 0 to infinity is going to be in my domain. For my range, I start from down here and I look up in the y values. Well, I go to -infinity here and I keep going, going, going. I'm still going to have values keep going and going and going. So actually the range of this function is going to be all real numbers. Now, the graph of the logarithmic function always passes through the point 1, 0. Maybe I should say of the original logarithmic function, with no transitions or no transformations whatsoever. And that is always going to be the x-intercept on the original, and there are no y-intercepts on a logarithmic function, and that's vice versa for our exponential. There's no x-intercepts, but there is a y-intercept. Now, the graph approaches but does not touch the y-axis. So here's my y-axis, and that's I already alluded to, that the y-axis, or the line x equaling 0, is a vertical asymptote. Okay, so you want to make sure that you have that down. All right. Now, 2 other functions that we're going to get in here that you're going to kind of practice with doing some of those is the graph of f of x equals the log of x, and f of x equals the natural log of x. So this is the natural log of x. Now, the thing about these, if you look at them, they do not have a base. When we write them like this and write them like this, if you look on your calculator for some logs, they have no bases on there like I had up there for log base 2. So I want you to remind you that this function, okay, is understood to be a base 10. So these 2 things are the same. They just remove the base 10, okay? When I get the natural log, this function is actually log base e of x. So this is the natural exponential inverse of that, okay? Referred to as the natural log. So the base that is understood here in this notation is that e. Now remember, e is approximately 2.718 when we looked at that number. And that, again, that's just a number, but there's actually much more application that you have of that in higher math, okay? So here is the graph of our natural log. So if I looked at some t-tables here, we would have the point 1, 0. We would also have the point 10, 1. So notice here is 1, 0. Here's the point 10, 1. Those are some guiding points. Remember, this is equal to the base that I have there. Here, if I looked at some points on this graph, we still have the point 1, 0. That's for every log in the original form with no shifts. But then we also have the value of 2.718 which is the e, and the y value would be 1. So if you look here, 2.718 is approximately here. That's where we cross at 1. This one is slightly above. So I put these in here for you just to kind of see those graphs, because in some of the transformations that we will see, we not only have log base 2s on some, but you will also have log base 10 of sums as well, okay? All right, very good. Let's try to graph some of these, and we're going to give the domain and range of each graph as well. Now this is again working with our transitions. We have to know that original function of base 2, so let me kind of graph that in there, 1, 0, and 2, 1. If we wanted to go 4, 2, we could, but this is the original log base 2. Now, what happens to that log base 2 of x when I have x plus 2? When it's grouped with my x, it is a horizontal shift. Take the opposite of what I'm looking at, so that means we're going to have to go left by 2. There is a vertical asymptote here, so that means that when I shift it over by 2, and some people like to do the original graph on there, some people don't, but when I shift it to the left by 2, this is my new asymptote that I have. Now remember, from this origin, this would be acting as my new origin, I'm going to go over to the point 1, 0. I'm going to go over my base and up 1. And if you wanted to do one more, you could go over, in this case with 2, over 4. 1, 2, 3, 4, and up 2. Okay, and this would be my graph. But again, I think the most important points that you have here is going to be kind of, maybe I do the quote points. So these are kind of your guiding points. 1, 0, and the base, whatever the base is, and 1. So in this case, our base is 2 when we have it. So make sure that you remember those key points. All right, what happens when I have this logarithmic function and I have a minus on that? If you remember, when we have a minus in there, that means that we do a reflection over the x-axis. Okay, so I again am going to do the original function, 1, 0, 2, 1, because that's my base, go over 2 and up 1. Again, if you want to do the square, I would go over 4 and up 2. So this is my original log function, okay? Now, I want to know what the reflection is. I'm going to change colors to do that. That reflection means that I need to, now, wherever I put a point, instead of going up or down, well, this one's on the axis, so if I reflect over the x-axis, it's still going to give me the same point. But this point here, 2, 1, instead of going over 2 and up 1, I'm going to go over from the origin 2 and down 1. This point, I would go over 4 and down 2, and then all of these points would match up here in that sense. So I still have a vertical asymptote, but I'm going to now, in a sense, be a decreasing function as opposed to an increasing function with that reflection over the x-axis. Notice here, if this is my mirror, notice I've mirrored it over that axis. Okay? All right, very good. Let's try the next one. Next one, I have a half in front of the original. So that means that I need half of the original values for that. So again, I'm going to kind of do that t-chart. We did this before with parabolas, but we've not done it in a while. So I have the points 1, 0, the point 2, 1, that's my base 1. And then for an exponential, I get a number of 4 with a base of 2, or a power of 2. With the power being 2, 2 squared gives me this 4 here. So when I have to take half of that, that means I need to take half of all these y values. So half of that is still going to be 0. Half of that is going to be 1/2, and half of this is going to be 1. So basically we're doing kind of a vertical shrink here. There's no movement left or right, no movement up or down, so I still have a vertical asymptote at x equaling 0. I still have the point 1, 0. Then I need to graph the point 2, 1/2. Then I need to graph the point 4, 1. So I have this point, and so we end up having it squashed, basically, as we go through there. Okay, now when in doubt, you can always plot points. You have the option to do that. Now here, I get, on this fourth graph, I have log of x plus 2. Now there's no base there. So remember, that is log of 10 of x. plus 2. So my base is actually 10 here. Now I'm going to go ahead and change these. I'm going to make this 2, 4, 6, 8, and 10. I should have got a better graph, but we're going to end up getting stretched out quite a bit because of our base of 10. So this plus 2 at the end, it is not like what we just had up here on the very first one. This is grouped with the x, so that's a horizontal shift. This guy right here is a vertical shift, so that means I'm going to have to move kind of my axis up 2. Now, that's not a horizontal asymptote or anything like that. I'm just moving that axis up. You want to do this. This is kind of my new axis that I can reference. So I'm going to change my colors to red so that I know what my graph is. Now, if we have a log function, I am going to have that vertical asymptote at x equaling 0. But again, this is not a horizontal asymptote. It's just my new axis. So for a log base 10, my points are going to be what? I'm always going to have the point 1, 0. Then I'm always going to have the point that is my base, comma 1. Okay? So at 1, 0 from my new origin per se, 1, 0 since I'm scaled at 2 is going to be right here. And then I'm going to go out 10 and up 1 to get that other common point. So if I do this, this now would be a sketch of log base 10 of x plus 2. Okay, so I've just shifted it all up twice. The original would be, let's see, would be something like that, okay, with the dash part. So we've just moved it up twice. All right. Now, the next one is dealing with our natural log, which remember is log base e of x, and then I have that plus 1. So the plus 1 is very similar to the one we just did. My new horizontal axis is going to be moved up. Here's the vertical because I'm not shifting anywhere left or right. We are still going to have a vertical asymptote at x equaling 0. And so maybe I should do one that has a horizontal and a vertical shift together, but this is good enough. We'll just do this one. And so we have to remember our key points on the natural exponential. Remember, that's what it is with the base of e. I always have the 0.10, but then my 2.718, which is approximately e, is my base, comma 1. So these are my guiding points for me whenever I'm now shifting it up 1. Here's kind of my new origin. If I go over 1, 0 from there, I get this point. If I go over 2.718 up 1, gives me this point. If you wanted to square e to figure out that number, I think it's like 7.36 or something like that, you would go out 7.36 up 2 would be that next point. But these are good enough. And again, with my lab math, I'm sure they're probably going to try to have you identify which graph matches with the function. All right, let's try this last one. And this last one looks a little bit different because that natural log goes second. And I have that 1 out here. So I'm going to rewrite this function as negative natural log of x and then plus 1. So it's very similar to what we have here. We still have a plus 1. So that means I'm going to have to shift it up 1. So here's my new axis if I want to have a guiding point for that. But I now have to do the negative of that. So here's my vertical asymptote again. So the points that I have for the original are going to be 1, 0, and then I remember we have that 2.718, and then 1. But instead of going up 1, now we want to do that negative 1. So I'm going to actually have a 2.718 negative 1. Okay, so from my guiding origin, I'm going to go over to the common point 1, 0. Unfortunately, there's no different point over that to be reflected over the x-axis. On the original positive natural log of x, I would go over 2.718 up 1. But since it's a negative, that means I need to go down 1. So I'm going to have a point that's right here. So we actually can reverse those again into a decreasing function for the negative of that. And that's a good sketch for that. Remember, negative in front does a reflection over the x-axis. Okay? All right, very good. Now this last chart that I'm doing for you is basically just a similarity between different bases and the common log rhythms. This is base 10, and this is our base E that we want to make sure that we remember. Base E, remember, is approximately 2.718. That's something you want to remember. So in general properties, when we saw some of these, log base b of 1, b to what power equals 1, it is equal to 0. With my base 10, what you will see is that you'll just see log of 1. That's going to be equal to 0 as well. And if we see the natural log of 1, that's going to be equal to 0 as well. Okay, so these are very similar. I'm just changing bases from a generic to base 10 to base e. What do they look like? If I have log base b of b, b to what power equals b? Well, it is 1. What will that look like here? That means that I have log base, or log of 10 is going to equal 1. And then I have the natural log of e. E to what power equals e? That is going to be 1 as well. Log base b of b to the x. Well, b to what power is b to the x? It is x. Then it would look like this for a base 10. Log base 10 to the x equals x. And the natural log of e to the x equals x. And this we use quite a bit when we're solving natural exponential equations, which we will do in another section. The last property, I have b to this power. So b to the log base b of x. Remember, they are inverses of each other, so in a sense they cancel themselves out. So I would just be left with x. What does that look like in a base 10? Well, that means I have 10 to the log of x has to equal x, because you don't write the base 10. And it would look like this, where I have my base of e to the natural log of x has to equal x as well. So these last two are ones that we will use quite frequently whenever we solve exponential equations and logarithmic equations. But for now, I'm just kind of putting those there for you. So let's do this idea here to figure out if I can answer these here using some of these properties. So here I have log base 10 that's invisible of 1,000. So 10 to what power is 1,000? Well, 10 times 10 times 10 is 1,000. Therefore, this answer is equal to 3. That's the power that makes that work. Here again, I have log an invisible 10. 10 to what power is 10 to the 8th? Well, that is incorporating, let's see, this. Here it is, this one right here with the base 10. Log 10 to the 8th power has to equal that power, which is 8. Now I have a base 10 to a log of 45. Well, remember, this power, or this base with this in the power, those logs and that exponential will cancel themselves out, leaving us just with the expression that we have there of 45. Natural log of e to the 7th. Remember, this is a base e. E to what power is e to the 7th? Well, the power is 7, so that's what we're answering there. The natural log of e to the power of 13x. Remember, the natural log and these e, according to this piece right here, they are inverses of each other. So in a sense, these cancel themselves out, leaving us with the power, which in this case is 13x. And to do kind of the reverse of that, where I have a base of e to a natural log in the power, these again are inverses of each other. They are going to cancel themselves out, leaving me with just an 8x. And those are going to be your final answers there on that. So again, nice little introduction to some logarithms, and so it is kind of a crazy little idea thinking about the powers and such, but you would have that incorporated with these properties and stuff. And just remember, when you're finding a log, you're looking for the power that makes that true. So we will kind of continue with this in sections 4.3 and 4.4. Past what we've done in here and kind of expand upon it. So we will wait for that. So until next time.